Hello, this is a video on for day 7 and 8 of Unit 4, which is Chapter 3. And this is graphing non-linear inequalities. So basically graphing the same shapes that aren't lines. That's what non-linear means. And inequalities, so an inequality greater than or equal to in this case, in this example, instead of an equal sign. So really, we just kind of want to, first of all, we want to be able to determine whether ordered pairs are a solution for an inequality. And all we do is just plug in x and y. So for this point, we plug in 5 for y and -2 for x. And we can simplify this side. -2 to the third power is a -8. And we have a times 2. This is a -16 plus 7 is a -9. So we have 5 is greater than or equal to -9. And just ask yourself, is that true? Is 5 greater than or equal to -9? Yes, it's true. So this one's good. And then 3n -1 plug in. -1 for y, and then 2 times 3 to the third plus 7. And you can kind of tell right now, this is a negative number over here. These are all going to be positive numbers, nothing making anything negative. And so this -1's not going to be greater than it, but we should follow it through. We'd get a 27 here. So 2 times 27, that's 3 to the third, plus 7. This is 54 plus 7. So 61. -1 greater than or equal to 61. No, that one is not a solution. So what this means in terms of a graph, and we're not there yet, but we'll get there in a minute, is that if a solution is, or if an ordered pair is a solution, it means it makes a true statement. This is a true statement. That means that it is in what's called the solution region. And so instead of just the graph of like a line or whatever, we actually have a line or a dotted line, and there'll be a shaded region, meaning that all of the points, any of the ordered pairs that are in the shaded region would also make a true statement when put into this equation. Oppositely, if you plugged in 3 -1, this point would, on the graph, it would lie outside of the shaded region because it does not make a true statement when you plug it in. That's the main gist of why we're doing this. And then briefly, we can burn through this one here. And so we just got to remember what absolute value means. And it just means that it is a grouping symbol. So it's like a parentheses. You would do that first. And you could throw away the brackets once whatever number on the inside, if it's negative, make it positive. If it's positive, it stays positive. Either way, you can throw away the brackets once you make it positive. All right. So we'll plug in 5,2 into this absolute value. And the -2 would be for y. Absolute value 3 times 5 minus 4. Absolute value bracket -1. We can simplify this. I'm really only working on the right side, so I'm just going to stop rewriting this and I'll save it till the end. This is 15 minus 4, and then -1 outside the brackets, which is absolute value of 11 minus 1, and then absolute value of 11 is 11. So we can just throw away the brackets, it stays positive. -1 is 10, and greater than. So -2 greater than 10. True or false? False. Okay, that's not true. It doesn't make a true statement, meaning 5 -2 is not going to be in the solution region, the region that's shaded in this graph, because we did not get a true statement when we plugged it in. So this is no. And we can do the other one. 0, 3. So 3 greater than absolute value. 3 times 0 minus 4, absolute value -1. This would be 3 times 0 is 0. 0 minus 4 is a -4. And the brackets are still there, but we can throw them away if we make this thing positive, positive, and we throw them away. And then 4 minus 1 is 3. So 3 greater than 3, that is actually also false. If there were an or equal to sign, obviously that would be true because it's not greater than 3, but it is equal to it. So it does fit the criteria of making this a true statement if there had a or equal to sign. It does not, so it's false. So neither of these points are in the solution region to this graph of an absolute value graph. All right. So here's where the graphing comes in. Those were just testing points to see, and it may be better to see in a visualization. There's a couple little things that we need to pay attention to. The type of sign that we have, if it's just less than or just greater than, they are dotted lines or dashed lines instead of just a regular graph like of a parabola or whatever. Here's a parabola. That's what we always did when we had like y equals x squared. If we had y greater than x squared, so it's no or equal to, it's just the greater than. That means that instead of having a parabola with a solid line, we would have a dotted line. Ultimately, what that means is if for some reason I found a point and it happened to be right on the line that the parabola curve is created by, if I tested a point there, it would not make a true statement. That's just the boundary line. So it's excluding the points that are actually on the line. And this should be a little out here a little bit. They're actually on the line. But anything in the shaded region would still be true. And so if we have y on the left side, or what you're solving to is on the left side all the time, then it's pretty easy to just use the rule. If it's greater than, you shade above. If it's less than, you shade below. So y greater than x squared, it's a dotted line because of greater than. It's not an or equal to. And then we would shade just in that region up there, contained by the parabola. Contrast that to if we had x is greater than or equal to x squared. So then that is a solid line because it's an or equal to. That means any point that I would test that happens to be right on this line that makes the curve, it would still make a true statement. So it is included in the set of ordered pairs that are solutions. And once again, since I have a greater than, y is greater than x squared, we would shade above the curve. There is other a couple rules we may not remember, and so it's good to go over it. This is just in each of these problems we have just a slight difference. You'll see these first two are very similar. The only thing that changed was the equal sign and the less than sign. And we'll see that what happens is really, well, one thing interesting happens, but compare this middle equation to this equation over here, and everything's the same except the sign of the 4. Okay, so the regular example here is just a regular equation that we can solve. You subtract 3, you divide by a -4, and you get a -1/2. Great. If we did the exact same equation, but an inequality with a less than sign, there is something funny that happens. When we subtract 3, that's fine. We divide by a -4. When you divide or multiply both sides by a negative number of an inequality, the inequality changes directions. So only by a negative. Multiply or divide both sides by a negative, your inequality changes directions. So we changed directions, and now it's greater than -1/2. It started as less than, but we divided by a negative, changed to greater than. That's just one thing we need to keep in mind. And we can see in this last example, it was a +4. Same problem, except it's +4 that we divide by. So we do not change. We do not change the direction of the inequality. So just with those in mind, but they may come up. So I'm going to go ahead and graph this on Desmos right away, just so we can kind of get a picture of what we're dealing with and how to do it. So y is greater than square root of x minus 5 plus 4. y is greater than, square root's down here, square root x minus 5, and then outside plus 4. So let's look at our graph. You can see it, and in our packet, we should get something that looks the same. Scale may be different, that's fine. Minus 5 plus 4 I put, right? Real quick, I just want to compare this to the parent function of y equals square root x and see how this differs. First of all, we have a dotted line, and that's because it's not an or equal to, it's strictly greater than. And since it's strictly greater than, we get a dotted line. We also, this is one of the weird graphs that it doesn't continue on, it just starts at 0 and goes off. So the solution region that is created with an inequality has a boundary of the y-axis, and it would make sense because if we plugged in if we plugged in anything negative for x, it'd be an imaginary number, and we wouldn't be able to graph it on a standard coordinate plane. So that's why the graph doesn't go farther to the left than 0 on the x-axis. And if we relate that to where we moved this graph, there was only translations that we studied. Inside moved it right 5, and then outside the plus 4 moved it up 4. So really all that happened was we took the vertex and we went right 5, up 4, placed it there. Everything else is the same except it's a dotted line, and we have shading. And the shading, it has a boundary here that we won't see in other graphs, mainly. A natural boundary. Again, because if I plugged in, like, let's say, 4 for x, notice anything, there is no coordinate in this graph, in the shape of this graph, that has the coordinate 4 or 3 or 2 or anything less than 5. And the reason is because if I plugged in anything like that, I would get an imaginary number. If I plugged in 4, I'd get -1. 3, I'd get -2. Underneath the square root, it's an imaginary number, so we can't graph it. That's why we have this innate boundary, innate vertical boundary that is unique to just this graph, this type of parent function. And because it's a shaded region, we have to take that into consideration. That means anything in this shaded region, any point in here that I plugged in for x and y in this graph would make a true statement. Anything outside or anything on the dotted line would make a not true statement. Okay, so it's important to to realize the difference between a dotted and a solid line. We could also, the parent function uses the ordered pairs 0, 1, 4, and 9. Because you're taking the square root, we want to use perfect squares. So that's how it would be easier to graph it that way, if we just use those ordered pairs instead of like 1, 2, 3, 4, 5. What happens is that for the translations that's happening, the x gets +5 because it's moving right 5. Remember, it's backwards to what we think. And the y gets added 4 because it's on the outside and it goes up 4. So if we change our ordered pairs, our standard parent function ordered pairs, these are the new ordered pairs we get, and that's what we graphed. So that's how you do it by hand. I personally would just say, oh, this is the parent function starts right there, bam, goes up that way. The new graph, it's an inequality, it's greater than, so I'm shading above, and it's a dotted line, but where do I put it? All I do is move the vertex right 5, up 4. That's what the translation is. So right 5, up 4. So it's right there or so, and it's a dotted line. It goes off that way. And then I just need to shade above it. So I'm shading above my new dotted line, but I have to be careful because this one in particular has a boundary right here where I won't cross, nothing to the left of that boundary, because anything to the left would be an imaginary number in our equation. Okay, so that was a fun one. This is a good one because we have a reflection. We haven't seen that yet very often with squared function. But we should know what it does. A negative number on the outside reflects our graph over the x-axis. So if I just started with the parent function, So I'll be kind of erasing this thing. Parent function starts like this, goes off that direction. First of all, the reflection, I already know now that this graph's not going to be, it's not going to be going up here. It's reflected over the x. It's going to be going down here. So that's just the first transformation that I drew. Okay, so now we know that so far. We also know that it's a vertical stretch by a factor of 2. So this is actually not going to be strictly going, you know, right, like this. If it's a vertical stretch, it's going to be kind of like you're stretching part of a rubber band, let's say, and this thing then in the vertical direction is going to be kind of expanded down. So it'd really be more like something like that. It's just stretched down a little bit. We also have an inside translation. So it's a +3. It means we go left 3. So after all of this, after all of these things that I've done here, left 3 now didn't go up or down. Left 3 is over here. So we can erase these other ones. Okay, so that's generally what our graph should look like. We need to know our boundary lines. The reason why I kept it a solid line instead of making it a dotted is because it's an or equal to. The or equal to means we include any ordered pair that is on the line. Then we see it's less than. So less than is shade below. Greater than was shade above. So shade below our graph. And so we're shading down here. But we have to stop wherever the vertical line meets our vertex. So wherever vertical line could be made that meets our vertex. So anything left of here is not in our, we can't shade over there. So it's not going to be true. If we were to plug in any point over there, we'd get an imaginary number, and we can't graph those on a regular plane. So, you know, we can test this out and just make sure we did it somewhat accurately. -2 root x plus 3. -2 root x plus 3. And I had to change the inequality to a less than or equal to. Less than or equal to. And I will. Okay. So as we see, we get the same thing we kind of drew. You notice what happens if you take away the 2, just so we can cover that a little bit better. That's taking away the vertical stretch, making it just regular and not stretched out in the y direction, in the up down direction. See that? It kind of makes it more squashed. But this is the actually regular amount. When you put a 2 out here, again, it's a vertical stretch or a vertical expansion. So in the y direction, it's expanded. You'd think of it as like kind of balloons out, puffs out a little bit in the y direction. See that? It's really cool. All right, so a good idea if you are doing this on Cami, you feel free to graph it on Desmos and just take a screenshot for the homework. That would be quick. Your learning will be deeper if you're just doing this by hand on paper. If you have that option, but graphing it by hand is doable as well. Just take the parent function, stretch it or compress it if you need to, flip it if you need to, and then translate it. And then the key thing is shading and then dotted or solid line. I do want to do, I got some space right here. I'll throw in an example I'm just creating right now. Let's just say we had something like, just so you see it, y is less than, just straight up x to the third minus 1. All right, so here's a graph. Here's what we know. The parent function has like the vertex kind of at 0, 0, and it goes up like this, and it turns right there and continues to go on like that after a curve. The only difference here is that it's translated down 1. So down 1 is where this would go. And we have a strictly less than, so it's a dotted line. And then we just need to know where to shade. Where to shade depends upon if it's greater than or equal to. If as long as we have y over there on the left, it'll always work this way. It's basically saying y values are less than my graph. So where my graph is, I shade below it. That also kind of means to the right, because we got to be below this graph. So anything, again, just to wrap it up in a nice little bow, any point that you could choose that is in this region, like, I don't know, let's just say 7,0 over there. If you plug that in, you would get a true statement in this. 7 going for x, 0 going for y. You simplify it, and you would get a true statement. If you plugged in 0, 0, you will not get a true statement. It's not in the solution region, and you could prove it. 0 less than 0 to the third is 0, minus 1 is a negative 1. That's not true. So that's how you can always tell where to shade. All right, I hope this made sense, and good luck.